Okay, so welcome everyone to the next talk, Who Gave the Toaster Root Access to the Physical World by Pete. Pete will be talking about the security of embedded devices, because embedded devices have access to a ton of personal data, and he'll talk about security mechanisms to prevent a hacked device from leaking all your data. So, huge applause for Pete, please.
Thank you. Welcome to this talk, the goal of which is to make you rethink the way in which we allow smart devices to access or interact with the physical world. Now, of course, in order to be able to rethink it, we first need to have an understanding of how we think about it today. So I'd like you to just take a moment to think about this question, right? So how do we secure smart devices today? And for some inspiration, I've added a smart door lock, an IP camera, a toaster that somehow needs to speak Wi-Fi, and a smart coffee maker. So how do we secure these things? I know that's a very open-ended question, but the way that I see it, what we typically almost always do is that when we consider the device in this very abstract way, where here on the left we have potential sensors and actuators, a way to interact with the physical world, and then next to that we have the smartness of the device, so the thing, like probably the code running on a microcontroller. Then we really have no limits on how the smartness of the device can use those sensors or actuators. And then if we do access control, we always put it here, after the smartness, between the connection, or on the connection between the device and the internet. And typically this access control is actually also implemented in the smartness. This works fairly well in many cases, but it has one fundamental problem, and that is that if an adversary can compromise the smartness, then that adversary can basically do with those sensors and actuators whatever it wants. And that introduces risk. And that risk can actually be greater than you would think, because there has been quite a bit of work in the past that shows that even very simple devices and very simple sensors specifically can be much more problematic than you would think. I brought two examples here today about innocent-looking sensors that can leak actually really sensitive info, or potentially really sensitive info. The first one is a reference to an academic paper that showed that if you just have data from a humidity sensor in a room, like you have in many rooms in commercial buildings or even in private buildings these days, that from that humidity information you can learn how many people are in the room. And if you then have that over time, you know when people enter or leave. And then there's this really cool paper which shows that if you just have information from a barometer, for example, the one that is in pretty much every phone that you buy these days. This actually, if you don't know this, it's like the accuracy of the barometer that's in most smartphones is like insane. But if you have access to that data and a person travels around a certain city, and then you overlay that barometric data with the height profile of that city, you can super accurately track the person holding the phone. And that's particularly interesting because this barometer is not considered a sensitive sensor. So applications can just get the data without needing an explicit permission for it. And then on the actuator side, actuations can just be plain dangerous. For example, when somebody can turn on a stove when everyone is asleep. Right? In a single case, that's not that likely to really lead to a dangerous situation. Probably there's just a hot surface. But imagine that you can launch this attack over a couple of thousands of devices at once. You know, there's a fair chance that on one of those stovetops there's a newspaper or something else that can catch fire. And given the nature of IoT devices and smart devices, it's really not that absurd to think that once you found a vulnerability in one, you can all of a sudden exploit a whole bunch of them. So this access to sensors and actuators is very problematic. Right? Is there something that we can do to prevent attackers from misusing this ability to sense and actuate, even after they have compromise the device. And more concretely, the question I asked is, hey, is there a way that we could shift left this access control? So can we take the access control that we normally only put between the smartness and the internet, and can we put a copy of that or a different version of that between the sensor's actuator, so the physical world, and the smartness? Because if we can do that, then if the adversary can compromise the smartness, they can still be blocked from interacting with the physical world. And I looked at this in a previous live, which was not all that long ago, when I was working in academics, and we proposed this model, and actually also implemented this, where what we do is we take an automation device, and we add a very small but powerful block to it, which we call the peripheral guard. And that peripheral guard has the ability to decide whether the device runtime or the smartness can actually access peripherals, yes or no. And we showed that you can implement this using very simple mechanisms. So this part here, you can implement with very simple discrete electronics components. And then that peripheral guard itself, you can also implement, for example, on a separate microcontroller that you would put in the product in a very simple way. And then you can, and then the advantage that you get from that, from the fact that you can implement this in such a simple way, is that it gives you what's called in system security a very small TCB, a very small trusted computation or computer base. And the advantage of a very small TCB is that it means that you only need to trust a very small amount of code or a very small part of the system to get the security properties if you want. And in the paper that we wrote about this, we actually showed how small this peripheral guard can be, and then how you can also leverage the smartness to be able to do things like formally verify parts of it, so you get like really high assurance levels on the security of the peripheral guard. Now, one problem is, of course, that this peripheral guard, it needs something to base its decisions on about whether access is allowed or not. And in isolation, that's very difficult. So a model that we propose is that this peripheral guard stands in context with what we call the central deployment manager, which you could imagine as a device sitting somewhere in your house that whenever a device runtime wants to access a peripheral, the peripheral guard would send a request to the central deployment manager, and the central deployment manager can then decide, hey, will I allow this interaction, yes or no? And the central deployment manager can then be more complex. It has a lot more context, knowing what is actually happening in your house or in your office. And based on that, it can make these decisions. And when you do that, you can get some very strong assurances, for example, that when you have cameras in your house, but you don't want those cameras to be able to film anything when you are at home, you could have a policy on your central deployment manager that says, hey, when I'm at home, never allow any interaction from the smart camera to its actual image sensor. You could also go a different way, and you could try to add more complexity anyway to the peripheral guard. So you would trade off some robustness, but you would be able to do more sophisticated things. And that's also something that we looked into and showed that's actually possible. And to do that, we looked at a class of device which I find very interesting, and that's smart speakers. Because smart speakers, they come with this inherent paradox, right? Because all of the smart speakers, they always promise that they will not listen to you except when they're being addressed, saying like, hey Siri, or okay Google. But of course, in order to know when they're being addressed, they need to be able to listen to you all the time. And smart speaker vendors, they solve this by having a small amount of code that always does the listening, that then only triggers the large bit of code when it actually triggers that you addressed it, or notices that you addressed it. But this has a problem because it really requires a very high level of trust in the honesty of the vendor to not spy on you. And even if you trust the vendor, they could still be incompetent. And so they could implement this mechanism insecurely, so if somebody can compromise the device, they could spy on you anyway. And this is especially problematic because we've seen in the past that these vendors are actually not that trustworthy as they would like us to believe. And I'm not sure if you recall this one, but a couple of years ago, there was this huge outcry in various media because it came out that pretty much all of the smart speaker vendors, it says Apple here, but there were similar articles about all the other ones, they had contractors and employees listen to pieces of recorded data in order to label them for training. And to the security community, this was not such a surprise, but for the public, this really was a breach of trust. And it led to headlines like this one saying, Apple contractors regularly hear confidential details on Siri recordings, workers hear drug deals, medical details, and people having sex. Now, of course, these product vendors, they're aware of this problem, and they try to mitigate it by having these status indicators on the device. There's an Amazon device, an Apple device, and a Google device, and they all have something that's supposed to show when they are actually listening, and when they're actually capturing audio. But when you try to find out how these mechanisms actually work, you don't find anything. And that probably means that it's not very secure and is just implemented in standard software, because if it would be secure, they'd probably all be bragging about it. So, can we do any better than that? And we could try to do better by basically using the mechanism that I described earlier, where we put a gateway, so access control, between the microphone and then the runtime with connectivity, so the smartness. But this has a pretty obvious problem that, well, the gateway doesn't know when the device is addressed. Because if the gateway would know that, there would not need to be any event detection, or there would know, the gateway doesn't know when the device is addressed, so it would have to provide access all the time so that the smartness can figure out when it's addressed. But if it needs to provide connectivity all the time or access all the time, then you might just as well not have a gateway. So something that we could try to work around that is we could put an isolated event detection container, so a sort of mini smartness, that sits between the sensors and then this gateway. And then we would allow this isolated event detection container to always access the sensor data, do its checking, see whether you said, OK, Google, and then when it detects such an event, it could declare that to the gateway. The gateway could then trigger a notification, something that you can see as a user. That could either be something that you can directly see, like actually illuminate these indicators on the device, or it could create a log that you can audit later. And at that point, it could allow access to the sensor data to the rest of the smartness. And it could actually try to process what it is that you said and what prompt that you gave it. This is already a lot better than the previous idea, but it still has a problem. Namely that we have no control over what data is stored in this isolated container. So if the code that's running here is malicious, what it could do is it could just continuously extract all the secrets that you're telling, for example, all the passwords that you're saying around this device, and then when a legitimate event occurs, it could generate a legitimate notification, and then it could smuggle out all of that secret data at once. And as a user, you wouldn't be able to tell the difference. So what you could do to deal with that is make that container amnestic. So build it in such a way that it's not possible to store any data in that container for longer than a certain amount of time. And this is also something that I've looked at and actually implemented and called it Kimya. So how does Kimya work? Well, it takes a microcontroller, and it splits that microcontroller in 5 memory regions. And if you know a bit about microcontrollers, then you know that basically everything pretends to be memory. So when you split the memory, you split everything else as well. These 5 memory regions are the sensor region, which contains the sensor, then 2 buffers, and a scratch region. These 4, they form the protected Kimya container. And then you have a 5th region, which is basically everything else. And then we introduce 4 different MCU phases. And these phases correspond to configurations of the microcontroller. In the idle phase, where execution starts and most of the normal code runs, there is read-write access to all other memory, but not to any of the sensitive information in this Kimya container. The code running in the idle phase, though, can request any arbitrary function to run in the acquire phase. And when that happens, the microcontroller is reconfigured to allow read access to the sensor and read-write access to a buffer. So this allows that code to take data from the sensor, potentially pre-process it, and then store it in that buffer. And then the idle code can also request another function, again an arbitrary function, to be run in the process phase. And when that happens, the microcontroller is configured so that there's read access to buffer A and B, and read-write access to scratch. And what that does is it generates kind of this unidirectional data flow diagram where data can flow from the sensors into the buffers and then into scratch, but the data cannot flow backwards and it cannot flow between the buffers. Now, when an event is then detected, which can happen in the process phase, then this user-generatable notification is made and the microcontroller is fully opened. This provides isolation. I said we also need amnesia. And that we can implement as follows, where every half of the lifetime, we swap buffer A and B. So we basically throw this switch in the data flow diagram. And then we wipe both the scratch region and the oldest buffer. This does two things. It ensures that no data in this container can be older than T lifetime. But it also ensures that we always have half of the lifetime of data history left, which is important because you want to avoid that you're saying, for example, hey Siri, and then this would happen between you saying hey and you finishing the word Siri, and that way your event would be fragmented. So it allows both data continuity, but also limits how old data can be maximally. We then also implement this on real hardware. And to do that, we used a fairly new technology. It's a couple of years old, but it's becoming mainstream quite quickly, called Trust Zone on Cortex-M. And to understand Trust Zone, you have to know that microcontrollers, they have different modes in which they can execute code. Right? So there's typically something called user mode and kernel mode, and then there's interrupt handlers. And then the microcontroller can transition between those modes based on certain conditions, and depending on which mode the microcontroller is in, it can then be configured to give the code access to different parts of the microcontroller. What Trust Zone on Cortex-M does, it basically doubles this, and it creates two worlds, a normal world and a secure world. Again, transitions between these two worlds are possible based on certain preconditions, and the secure world can configure which resources in the microcontroller the normal world has access to. So we can use the secure world to build a supervisor that can basically reconfigure the microcontroller in these 4 different Kimia phases. And that way we can create this isolated container. There's a lot of things that you can know about this or that you can read up about. And if you're interested in this, I really recommend this online book, embeddedsecurity.io, that goes into a lot of very interesting details about how this works on the low level. Guaranteeing this isolation is actually still a very difficult problem. And that's because of the possibility of so-called covert channels, which are channels that an attacker could use to try to communicate between 2 different processes, even when you're trying to avoid that. To give an example of that, let's say that we have some code that's running in the normal world in idle, that we want to be isolated from the code that's running in the Kimia container. And so formally, we ensure that there's perfect isolation. There's no way that these 2 can pass variables and so forth. But an attacker could still do this. In the normal world, before they start a call into the Kimia container, they could just store a timestamp. Then they call into the Kimia container, which reads sensor data. Then does some magic to extract secrets from that sensor data. And then encodes that secret in the runtime of this function. Yeah. Then when this function returns, the normal world, it takes a timestamp, and it can decode that information from the measured runtime of this function again. So even though we don't have any variables passing or nothing happening explicitly in memory, there's still a way for the normal world and the isolated world to communicate with each other, which is problematic because it's exactly what we're trying to avoid. Now, there are ways that you can avoid this, and for example, in this very specific case, what you can do is you can let the normal world declare for exactly how long it wants to transition into the isolated space. And then you can make sure that you always put the microcontroller in this isolated container for exactly that amount of time that was specified. So basically, it ensures that the delta between start time and end time will always be the same. There's a bunch more very interesting difficulties that I don't have time to get into, but we did actually build this, right? And we built this with real code actually running speech detection. It drove my partner crazy because I trained it on the simplest word I could imagine. I trained it to recognize my voice saying the word cat. And I have said that word thousands of times during this development and testing process. So what we did is I basically took a machine learning model that would detect me saying the word cat. And then I ran that on this microcontroller on the left, which is a fairly low-powered microcontroller, just in a vanilla version. And then I also wrapped it in this Kimia framework and ran it on the microcontroller on the right. Exactly the same board, just different configurations. And then both of those two boards are connected to the same microphone, so they see exactly the same input data. And what we saw is, well, first of all, no additional hardware is required, because many microcontrollers these days, they come with this trust zone functionality. And then we saw that there was also no loss in accuracy of detection, so the output of these event detection this event detection code was exactly the same. The only difference was that the version with Kimia added around 1.19 milliseconds of latency, which for these kind of applications really is negligible. And even more important than that is that overhead that was very stable. So when you're trying to write a scheduler or you're trying to optimize your code, it's very easy to take that into account. And I think this is really cool because it shows that actually it is possible to have way more strict rules on how you allow code or devices to interact with the physical world, while still giving you flexibility to do advanced tasks. And because, for example, Kimia, by not restricting which code can run in this acquire and this process phase, it means that you can still update the device and you can change the event detection code whenever you want. And with that, I would like to conclude with this observation that access to the physical world is really the key risk inducer for automation systems, because without that, it would just be any other piece of computing or device that's able to compute that we have laying around, and we have a lot of experience with how we need to secure those. And I also really want to push this idea that sensing and actuation, it really should not be considered as a commodity, as something that you can just do freely and that has no cost, but it should really be considered as a privilege and as something that should only be done when it's really needed. With that, thank you.
Okay.
Do we have time for questions?
Yeah, okay, I didn't recognize you were done. Yeah, so thanks a lot for the great talk, Pete. What? 2 minutes. Yeah, you still have 2 minutes left, so I didn't want to...
Okay, does anybody want to ask a question?
Yeah, 2 minutes for questions. There are the microphones. I think the one in the front and the back is connected. So if you have a question, just queue up there. I see someone running to the mic.
A queue of one is a queue, right?
That counts.
So, yeah, I was wondering, so now you made your prototype by you training your network.
Yeah.
So how would you see this being adapted?
Yeah, so The design is, of course, the design was really made to be as little restrictive as possible. Of course, when you want to put this into a real system, there's still a lot of tweaks that you need to do. But the main thing that we really show here is that, hey, this is actually possible.
Yes.
And so it's
yeah, I understand. I mean,
yeah.
no offense. I mean,
Yeah.
I really like the idea. But I was just looking like, how do you see this?
Yeah, so there's a couple of challenges. For example, one thing is that when you look at actual commercial devices, they will typically not have one piece of event detection code, but they will have it staggered. So they will first have something that is very low on resources, but that has a high false positive rate. And then whenever that piece of code, it detects that you addressed it, it will hand your code to the next piece of code, which will be more resource intensive, but a lower false positive rate. And some of these speakers will even then eventually take the audio sample, send it up to the cloud for a last check where you really have all the resources you want, and then make that decision. I believe there's also devices that can do this offline, so that don't use that step. But this is, for example, one thing that we would still need to look at. Okay, how do you deal with that? Because also when you have this multiple stages in a pipeline, that makes it harder to enforce that the detection always takes the same amount of time, for example. So it's in no way a solved problem, but I really believe that this is something that is worth looking into in more detail and changing the way that we think about this. That it's just a given that you can.
I agree with that. So thanks.
Thank you.
Okay, so sadly that's all the time we have. Thanks a lot for the great talk, Pete, and